The graph of a rational function. So chapter 4, section 3. So let's talk about analyzing the graph of a rational function. Again, this is going to be a wordy slide, but there's a lot to discuss here. So 1, factor the numerator and denominator of R, find the domain of the rational function. Remember, the domain comes from the denominator. Write R in lowest terms. Find and plot the intercepts of the graph. Use multiplicity to determine the behavior of the graph of R at each x-intercept. Find the vertical asymptotes. Graph each vertical asymptote using a dashed line. Determine the behavior of the graph of R on either side of each vertical asymptote. So remember, our domain is going to tell us where these asymptotes are. Find the horizontal or oblique asymptote if one exists. Find points, if any, at which the graph of R intersects this asymptote. Graph the asymptote using a dashed line. Plot any points at which the graph of R intersects the asymptote. Now, I know that sounds a little strange. It says find the horizontal or oblique asymptote if one exists. Find points, if any, at which the graph of R intersects this asymptote. And you're going, wait a second. That doesn't make sense. The idea of an asymptote is that it never touches it. Well, yes, that's true. But it's more you're looking at the end values, the end behavior as you're approaching x equal to negative infinity or x equal to infinity. For that asymptote, there can be places in between where you actually cross over the asymptote. So it seems a little strange in that, but when you start looking at the different graphs, you go, oh, okay, I get it. That's determining end behavior, not necessarily what happens in the middle. Then find the horizontal or oblique asymptotes if one exists. Okay, graph the asymptote using a dashed line. Plot any points at which the graph of R intersects the asymptote, as I just said. Use the zeros of the numerator and the denominator of R to divide the x-axis into intervals. Determine where the graph of R is above or below the x-axis by choosing a number in each interval and evaluating R there. Plot the points found. Now, you've probably done this before, and that's what you did. You said, okay, so you get all the roots or zeros of the numerator and the denominator. You use all those to create intervals starting at negative infinity going to positive infinity. And then you check each of these intervals to see whether you get a positive or negative result. One of the really nice things is we know about multiplicity now. So by using multiplicity, we can determine without having to do any calculations, once we know one sign in one interval, we can determine all the signs of the other intervals without having to go through and plug in more numbers, which makes our life really nice. And then use the results obtained in steps 1 through 6 to graph R. So let's analyze the graph of a rational function. If we have R of x is equal to x squared minus x minus 12 over x plus 5. Well, first thing I'm going to do is I'm going to factor out the numerator and the denominator so I can get my zeros, right? So I see that I've got x plus 3 and x minus 4 in the numerator and x plus 5 in the denominator. Well, if x plus 5 is in my denominator, I know that I can't allow x to be equal to negative 5. So we have our domain as x such that x is not equal to negative 5. We know that the value of the rational function will be equal to 0 when either of the factors of the numerator are equal to 0. So we know we've got x-intercepts at negative 3 and 4 because x plus 3 set equal to 0 means x equal to negative 3, and x minus 4 set equal to 0 gives us x equal to 4. So that's when we're going to have x-intercepts. And our y-intercept, just looking back at that original function again, if x is equal to 0, it's going to eliminate all these terms. We're just left with negative 12 over 5. So we have our x-intercepts we have our y-intercept. So now let's determine our vertical asymptote. Remember, we said the domain is going to create our vertical asymptotes. We know that x is not able to be equal to -5, so therefore we're going to have a vertical asymptote at x equal to -5. Now, what about horizontal and oblique asymptotes? Well, we look at the original function and see we've got x squared over x. So the numerator has a degree 1 higher than the denominator, meaning that we're going to have an oblique asymptote. And that oblique asymptote is going to be found by taking x squared minus x minus 12 and dividing it by x plus 5. And remember, as we do that, we will get rid of the remainder, whatever it happens to be. And by doing that, we come out with y is equal to x minus 6. So that's just use synthetic division or long division. I'm not picky about which you use, but just divide it and you'll find x minus 6. You'll have some remainder involved. Just ignore the remainder. It's not part of it. And we find that that does not intersect anywhere on this particular situation. And then don't ask me why it gave me a 1 again. That should have said 6. But we now go from -infinity to -5. Remember, we're creating these intervals. So I'm using my zeros of my numerator and my denominator. So from -infinity to -5, from -5 to -3, from -3 to 4, from 4 to infinity. And I personally go for the easiest one that I can, which is plugging in 0. 0 makes my life really easy. And we actually already did it because we found that the y-intercept, when x is equal to 0, we got -12/5. So I know the interval from -3 to 4, the sign is negative. Since I know that's negative and I look at all of my zeros and realize they all have degrees of 1, they're odd multiplicity, then that means that the sign is going to change at each of those values. So if -3 to 4, that interval is negative, then 4 to infinity is going to be positive. -3 to -5 to -3 is going to be positive. If -5 to -3 is positive, then -infinity to -5 is going to be negative. So therefore we have negative, positive, negative, positive. So all I did was start it out with 0 here, easy thing to find, told me it was negative. At 4, we have a multiplicity of 1, odd multiplicity, sign's going to change. And -3, multiplicity of 1, odd multiplicity, the sign's going to change. And -5, odd multiplicity, sign's going to change. And that allowed me to determine what was going to happen there. So now what do we want to do? Well, we want to graph our asymptote, so x equal to -5 and y equal to x minus 6. We've got our intercepts, so we want to plot those. We know where it's positive and negative, so we're going to use that to help us. And by doing all of that, we come out with the following graph. Notice my blue dotted line is my vertical asymptote at x equal to -5. My green dotted line is my oblique asymptote, y equal to x minus 6. We are negative from -infinity to -5. We are positive from -5 to -3. We are negative from -3 to +4, and we are positive from 4 to infinity. So it's just a matter of putting all these pieces together, and it is a number of pieces. You've got to do a lot of work to go through this. But if you take each one of them a step at a time, none of them are difficult to do. We just have to make sure that we do all the steps, and then we'll be able to draw the graphs. And you'll be amazed at the rational functions that you're able to draw and get relatively close to what they look like without using any fancy materials to do it. So that's graphing rational functions.